Hello everybody and welcome to the full presentation of our paper, A Code-Efficient Process Scripting Language. Let's start. So, what is the motivation behind our work? Imagine you want to implement a business process management system in a company, or you want to deploy a new process onto your existing BPMS. In order to do that, you need the model of this process. It should be an executable process model. It should include the essential control flow constructs to describe your business logic. It should also cover processing of the data during the execution and handle the communications, for instance, with external parties or external systems. In addition, the model should be clear and understandable for both the developers who would work with the low-level issues such as data processing, as well as for the domain experts who are responsible for the business logic. So if we want to build such a model, what are the available alternatives? First, there is BPMN. It is a visual language, it is standardized and highly adopted, it is very easy to use and to read, but it has a major drawback, namely it doesn't allow to model data processing in a structured manner. Second, there is business process execution language. It is code-based, it is also standardized, and it also supports all the major control patterns, and in comparison to BPMN, it also supports data processing. But it's harder to read and to use, and more importantly, is discontinued. Finally, there are the emerging process modeling languages such as AWS State Language, Uber Cadence, and Netflix Conductor, but they also have some limitations. Namely, they are code-based and some of them even have no graphical editor at all. They have significant gaps in control flow pattern support, and some of them run under the assumption of a closed ecosystem, meaning that they do not allow any interactions with external systems. Formalizing the requirements for a business process modeling language, we have arrived at the following ones, namely efficient syntax, control flow support, data processing support, and event processing support. We also evaluated the existing languages against these requirements, and as you can see in the table, all languages have their own advantages and disadvantages, and there is no language so far that would totally cover all the four requirements at the same time. With these requirements in mind, we have decided to build a new process scripting language that we call FactScript. When designing FactScript, we have focused on the following properties. First, we wanted it to have an expressive control flow support. We know that BPMN, for instance, supports the majority of control flow structures and is highly standardized and widely adopted. It has control flow elements such as sequence, parallel split and sync, choice and merge, including multiple choice and merge, as well as event-based choice. This is why we took BPMN as a reference for this property. Second, we wanted our FactScript to provide expressive data processing. We wanted it to have type safety, similar to programming languages such as Java and C#, and we also wanted to have general data processing capabilities. This is why we based our FactScript on Kotlin. Finally, we wanted the expressiveness of messaging and event handling. FactScript should support send, receive, and send-receive behavior and give the user the opportunity to wait and react to message events and timer events. We used BPEL as a reference for this property. Now to the structure of FactScript. On the highest level, any process definition in FactScript consists of three major parts. The first one is the API. API defines the type of the message that initializes the process and also gives a promise on which message types will be returned in case of success or failure of the process. The next part, and the most important one, is the execution. Execution contains all the process logic, meaning all the activities and events that are taking place during the process execution. The final part of a process definition in FactScript is a report. The report involves sending a message to a calling entity, signaling that the process is over. Note that the type of the message emitted in the report must correspond to the one promised in the API. FactScript offers extensive support of message and event handling. This is done with the help of the elements shown in this slide. Let us describe them in more detail. First, let's look at the emit element. The emit element allows the user to program sending a simple message. It would correspond to an intermediary message throwing event in BPMN. Next, there is the await element, which allows the user to program the process to wait for some event, be it a message event or a timer event. First is a construct that implements an event-based gateway. It allows you to create different branches of your process, and only one of the branches will be started, namely the one whose event takes place first. You can see it in the example below. Depending on whether the payment approval event comes in or 2 weeks pass, the first or the second branch will be activated. The issue command is used for asynchronous calls and would be translated into a send task in BPMN. Finally, the report represents the obligatory last part of every process definition, and it corresponds to an end event, allowing the user to specify successful or unsuccessful completion of the process. FactScript also provides support for the major control flow patterns. This is done with the help of the elements shown in this slide. The but element, for instance, is appended to an activity call and allows the user to specify the possible failures of an activity and the ways to recover from them. This element would correspond to a boundary exception catching event in BPMN. The execute all element allows parallel execution of multiple branches and thus would correspond to a classical parallel split and sync gateway in BPMN. The select element allows the user to specify the execution of one or multiple branches based on a predefined condition. It would correspond to an exclusive or inclusive OR, depending on how many conditions can be met at the same time. In the example below, select allows to execute one of the two branches depending on the state of the confirmed variable. Note that you can also specify a default path which is executed if none of the conditions is met with the help of the otherwise word. Finally, there is the repeat statement, which allows you to execute an activity or a subflow multiple times until some condition is met. It is very important to note that FactScript is not just textual syntax for BPMN. The structural elements of FactScript represent various control flow patterns, and the BPMN elements used in these slides are just the most common way to talk about these patterns. It is true that FactScript can be naturally translated to BPMN, but it is a process scripting language on its own, and it can be translated not only to BPMN. The implementation of FactScript has the following architecture. On the highest level, it consists of the two entities, IntelliJ IDEA and Camunda BPMS. The first element, IntelliJ IDEA, is responsible for the process development and also partly responsible for its execution. It provides the FactScript modeler, which is where you actually script your processes. This modeler uses IDEA's standard text editor and the constructs defined as Kotlin classes in FactScript construct definitions. It also provides the translator, which transforms the process definition in FactScript into a model suitable for the execution engine. In this case, into BPMN, usable for the Camunda BPMs. This entity also includes the listeners which interact with the execution engine. Finally, Each activity in FactScript is implemented as an external task from the point of view of the execution engine. The second top-level entity in this implementation is Camunda. It must be noted that FactScript by itself is not bound to any specific execution engine. Thus, it doesn't necessarily always have to be Camunda. Still, it is the case now. Camunda uses the process models provided by the translator and provides an execution engine which orchestrates the process instances, activates the listeners, and executes the activities. In order to evaluate FactScript, we have performed a case study with a real-world business process that is shown in this slide. The process starts when a payment has to be retrieved from the customer. First, the amount is withdrawn from the customer's account. If the payment is not fully covered by then the credit card of the customer is charged, possibly multiple times, until the payment is fully covered. If the credit card is expired, the customer is given 2 weeks to update the credit card details. If it doesn't happen, then the payment fails, and if some money was eventually withdrawn from the customer account, this money is credited back. This slide shows the definition of the very same process in FactScript, and as you can see, this definition is very compact. In addition, you have to define the variables used in this process in the very same file. You also have to define the types of the messages that are exchanged during the process, and last but not least, some direct manipulations to the data that are necessary in the process. Based on this case study, we can evaluate FactScript against the requirements we have defined in the beginning, starting with the first requirement, efficient syntax. We evaluated the grammar of FactScript based on different metrics, such as number of terminal and non-terminal symbols, effort required to understand the grammar, and the complexity of the grammar. We compared FactScript to different programming languages, such as Java and Kotlin. As you can see, FactScript demonstrates a much lower complexity than the general-purpose programming languages, which also means that FactScript will be much easier to learn. We also did a lines of code comparison between FactScript and BPMN. As you have seen in the previous slide, the process definition in FactScript took only 33 lines of code. It took additional 27 lines to define the variables, message types, and direct data manipulation, which sums up to 60 lines of code. In comparison, BPMN needs 429 lines of code to model the very same process. Although this comparison might seem unfair, since BPMN is a visual language and is using a graphical editor, it still provides the first insights on the compactness of FactScript. It is also still meaningful to do these calculations because the emerging process modeling languages also lack graphical editors. As for the second requirement, the extensive control flow support, our case study has shown that FactScript provides all major BPMN constructs. Regarding the third requirement, support of data processing, our case study also showed that FactScript allows the user to hold different variables of different types and also directly manipulate the variables during the process execution. Regarding the fourth requirement, support of event processing, our case study process involves sending and receiving events and commands. It also has start, end, and intermediary events, and has time and error events, showing that FactScript supports all these kinds of events. In our work, we have defined the requirements for a process scripting language. These requirements are code efficiency, control flow expressiveness, data processing support, and event processing support. To address these requirements, we have designed FactScript based on Kotlin. To evaluate FactScript, we performed a case study using a real-world business process. We also defined the directions of our future work. First, we would like to perform a user study with the developers. Second, we want to extend FactScript to use different execution engines, such as AWS step functions. Finally, we are also looking into deploying processes written in FactScript onto blockchain. Thank you for your attention. If you have further questions about this paper or FactScript in general, please contact me using the email address you see on this slide.